Hello everyone, welcome to another interesting lecture on digital signal processing. In today's class, we are going to talk about the frequency response of your FIR filter. In previous lecture, we have seen what are the types of your FIR filter, and we have divided or classified your FIR into four types: symmetric even, symmetric odd, anti-symmetric even, and anti-symmetric odd. So in today's lecture, we are going to talk a little bit more about these four types of FIR filters in terms of its frequency or magnitude response. So the frequency response or the magnitude response is computed in the frequency domain. So what we are going to do is we are going to take the symmetric time domain FIR filter or your anti-symmetric time domain FIR filter, which are given by h of n is equal to plus or minus h of m minus 1 minus n. So the symmetric means the first half of your response of your filter is going to be equal to the second half of your filter, and your anti-symmetric means the first half of the filter is going to be equal to the negative of the second half of the filter. Since both the symmetric and anti-symmetric are just differ by a plus or minus, it only makes sense to derive the frequency response of the anti-symmetry and the symmetry together. So that is what we have seen. And the first line I have written generalization of h of n is equal to plus or minus h of m minus 1 minus n. So that is to include both my symmetric and anti-symmetric response derivation in a single variable, in a single calculation I can show you. So now I am writing the h of z. So this is my FIR representation. So my FIR representation in time domain is given by h of z is equal to h0 plus h1 z minus 1 plus h2 z minus 2 plus h3 z minus 3 plus etc. hm minus 1 z of minus m minus 1. Alright, so this h0, h1, h2 etc. up to hm minus 1 represents your FIR filter coefficients. So these are the values, these are the filter values. So you have an FIR low pass filter, so your filter must have some values, right? So those values are this h0 to h of m minus 1, and this z inverse and z to the power of minus m minus 1, that represents your position of this h of n. They are more of the indexing for your h of n. So it just means that your h0, h1, h2, h3, etc. h of m minus 1 means your filter is positioned at places 1 to m minus 1, and that is represented by this z or the z to the power of negative. Good. So now from this FIR representation equation, what I'm going to do is I'm going to induce symmetry, because we are talking about the four types of FIR filter, and the four characterization for FIR filter depends on the first symmetry and anti-symmetry, and the second one is the whether your m is even or odd. So the length of the sequence, which is given by in this case m minus 1, so where that m can be either even or odd. Depending on that, your symmetry will be either odd symmetry or even symmetry. So everything is around symmetry. So everything has to do something with symmetry. So in order to introduce the symmetry, or in order to induce my symmetry in this generalized Fourier equation, that is h of z, what I have done is I have taken z to the power of minus m minus 1 by 2 outside. So that z to the power of minus m minus 1 by 2 is my center of symmetry, right? So that will be the middle element, that is the center element. M minus 1 by 2 will be the center element, and I'm thinking that that is the half where my symmetry starts. So after that element, I will either have a positive value, means the same symmetry, or I have a negative anti-symmetry. So that is why I've taken that z to the power of minus m minus 1 by 2 outside. So when I take that minus m minus 1 by 2 outside, then what happens is every term inside gets multiplied with this z to the power of m minus 1 by 2. So that is how I induce my symmetry into that equation. So if you take that equation, z to the power of minus m minus 1 by 2, then I induce symmetry in all the terms, because every term you see on the inside is having z to the power of plus m minus 1 by 2. Good. So now that is your symmetry computation. Now I'm just showing you some calculations here. I'm just expanding that two terms because I have z minus 0, z m minus 1 by 2, z minus 1 m minus 1 by 2. I'm just expanding it and showing you how the things are going to look like. And I'm going to show you another generalization. So we can write in this form and we can do the computation. But a more compact or a more convenient representation is when I can write these as my m minus 1 minus n. So I'm going to show that. So these are some of the values that I'll be getting. So now I can, here I may show you something. This is what I want to be using. So I'll write the generalized expression with symmetry. So now here I have induced my symmetry, and each term is having that symmetry induced in the form of z to the power of m minus 1 by 2. And now that is given by z to the power of m minus 1 by 2 into, see, I'm writing only those internal z terms inside the bracket. And then I can, what you can see is, if you see this, I'm having 0 to m minus 1, right? So that is the sequence I'm saying. And I can write now this to be z to the power of m minus 1 by 2 into z to the power of minus n. So this is what I'm using. And I'm generalizing it for n equal to 0 to m minus 1. And that is going to be written as z of m minus 1 minus 2n by 2. So I'm going to take this forward and I'm going to represent my h of z using this simplified expression. So my h of z, when I get to it, my h of z is going to be using the new simplified form. I can write that to be h of m minus 1 by 2. So I'm going to show you once again. Yes, so here my m minus 1 by 2, will not have any term because that's going to come to be z to the power of 0. And the rest of the terms are going to be there. Z of m minus 1 minus 2n by 2 plus or minus z of m minus 1 minus 2n by 2. So here when I make this m minus 1 by 2 and m minus 3 by 2, so I'm just taking this m minus 1 by 2 outside because that term is going to be z to the power of 0, and that's not going to have any z coefficient. That's going to be the middle term. So I'm just taking that outside. Okay, good. So with that, I can write the simplified form to be z to the power of m minus 1 minus 2n by 2. So I've just taken the h of m minus 1 outside, m minus 1 by 2. Now, let's see an example for my m is equal to 5. So I'm going to plug m equal to 5 in this equation. So what will happen is m minus 1 by 2 is equal to 2 and m minus 3 by 2 is equal to 1. And then I just play this, right, I will just see how my equation now turns out to be z to the power of minus 2 into h2 plus h0 z square plus z minus 2 plus h1 z1 plus z minus 1. So let us see this this one. Let us expand this again. So I'll open the bracket now, and that is going to come to be h2 z of minus 2 plus h0 z. Okay, so now this is my FAR representation. So now you can look at this also backward. Like if I start from this equation, so if I start from my h of z and then I go backward, I reach my h of z. That is the representation given in M form. So I can go from top to bottom or I can go from bottom to top. So I've shown you the top to bottom method for the derivation. That should be good. So these are the coefficients. And if you see the symmetry now, first half of the signal is equal to the second half, and my center of symmetry is at h of 2. So this is a symmetric odd because m is equal to 5. So similarly for my anti-symmetry odd, that is when m is equal to odd, I will have my first half of the signal or first half of the FIR must be equal to the negative of the second half. So in this case, I'll be having this to be h of 1 z to the minus 1 plus h of 2 z to the power of minus 2 plus this. And then you can see here my first half of the signal is equal to the negative of the second half of the signal. Good. So for m is equal to odd, I am writing my final expression, my final FAR representation for my symmetric and anti-symmetric m is equal to odd to be this h of m minus 1 by 2 plus n0 m minus 3 by 2 h of n into z to the power of m minus 1 minus 2n by 2 plus or minus to the power of minus. So this is the equation that you need to remember. And here I'm covering two types, right? So I'm covering my symmetric m equal to odd and my anti-symmetric m equal to even. So for my anti-symmetric, only the middle term should be, instead of plus, it should be minus. So I can just put that plus or minus there. And now this is my type 1 and type 3 filters. So this is my type 1 and type 3 FIR representation, and it is not still the frequency response or the magnitude response. So we are going to see that next. So first we will write the FIR representation in terms of the time domain coefficients h of n, and then after we do that, then we will go on to take the magnitude. We will go on to finding the magnitude of that h of z, and that is going to be your magnitude response or your frequency response. Now let's take the next case. The next two cases, my symmetric even and anti-symmetric even. So we have these two cases, and then what happens is my z of minus m minus 1 by 2. And now what I can tell you that the symmetry term, the inducing symmetry is the same as before, that is z to the power of minus m minus 1 by 2. But if you compare it with the odd expression, what you can see is your h of m minus 1 by 2. That disappears because the center of symmetry in your case of even, the center of symmetry doesn't pass through any samples. It just passes through a no man's region. It just passes through a region which is not having any sample index, right? So that is why your h of m minus 1 by 2 is not present in this expression. So this is how this example will make it clear for you. So for my m equal to 4, you can see the center of symmetry just passes through, it just passes through the center, and it is not passing through any of the indexes like minus 2, minus 1, minus 1, minus 2. Good. Indexes or the values. So that is why for your anti-symmetry, so hence even symmetry and anti-symmetry, you have this h of m minus 1 by 2 equal to 0. Clear? So if that is the case, then our expression now simplifies to that. And now let me see an example for m is equal to 4. That is the smallest even. I don't want to do m equal to 2 because that I cannot show much with that. So let me take my m equal to 4 example, and then I'm going to put it on this equation. So my n is equal to here 0 to m by 2 minus 1. So you have to just know these summation bases, because before it was m minus 3 by 2 in our previous, and now when m is equal to odd and when m is equal to even, so you are having your m by 2 minus 1. Good. And now I'm going to take this example. I'm going to put it for m equal to odd, sorry, m equal to even, and then I'm going to see what my equation for my FIR filter turns out to be. So I get my z of m minus 1 by 2 to be z of minus 3 by 2. Then plugging in the values and expanding, so I'll be getting something like this. So let me write it for you. This is z of 3 by 2 plus or minus z of minus 3 by 2 plus h of 1 by 2 plus z of minus 1 by 2. Good. So now when I open this, I'm gonna get it to be h of 0 into z of 0 plus h of 0 into z of minus 3 plus h of 1 into minus 1 plus h of 1 into minus 2. And that is going to give me my symmetry. So let us see, h of 0 plus h of 1, this becomes 1 minus 2 minus 1, then it becomes h of, let me just again get h of 1 0 minus 2 plus h of 0, and I get it as 0. Okay, good. See, now it is symmetry. You see the first half to be equal to the second half, and that is your symmetric even. And for my anti-symmetry, the first half is going to be equal to the second half, right? The last two terms are going to be negative for m equal to 4. So I'll write that also. So now with this, I can now write the generalized expression for my FIR filter, which is even symmetric and even anti-symmetric. So that's going to be something like z to the power of minus m minus 1 by 2, right, into sigma n equal to 0 to n by 2 minus 1 into z to the power of m minus 1 minus 2 n by 2 plus or minus z to the power of m minus 1 minus 2 n by 2. So you have to memorize this. It is in my head all the time. So for your exams and for your solving numerical of these types, you need to write these equations, and so that you can get started right away. You don't have to derive this and then start your numerical. Okay, so that is the good thing about remembering this boxed formulas. That now this is your FIR generalized representation for symmetric and anti-symmetric m equal to even. So that will be our type 2 and type 4 filter. Good. So that's about the FIR representation. So we have done that for all 4 types. Now we are going to do the frequency response. So we are going to take the magnitude of these equations that we have written. So we have written 4 equations with this plus or minus. We have 4 equations, right, for m odd and even. So we are going to take these 4 equations and then we are going to find their magnitude, and that's going to give me my magnitude response or the frequency response. And how do I do that is, I just put my z is equal to e to the power of j omega. So I put my z is equal to e to the power of j omega, and that is going to, what it is going to do is, it's going to bring my h of z to h of omega. So it's going to take my z plane representation of my FIR to the omega plane representation. So it's going to do that z to omega conversion, and when it does that, then what I have to do is I have to see what is the magnitude of that representation, and that's going to give me my magnitude response. So let's see how we are going to do that. So this is m equal to odd. So I have made a small mistake there. This should be m equal to odd. That because this is the expression for m equal to odd. What I'm writing here is for m equal to odd. And then I'm going to put in here my z is equal to e to the power of j omega, right? That's exactly what I'm going to do. So that makes my h of e to the power of j omega is equal to e to the power of minus j omega to m minus 1 by 2. Okay, so I'm just keeping that minus inside. Okay. I think again there is one plus sign there. Maybe I should write, but no, I get it right in the end. So I know that much because since I know the final formula, so that is why I'm very careless with these steps. So there are 2 mistakes here. I'm acknowledging that here, so I thought so that I'm not writing it on the board here. M is equal to even, and my here it should be minus m plus 1 by 2. Okay, but that is pretty much what's done. I'm not going to touch that part of the thing. I'm only interested in this e to the power of j omega plus or minus e to the power of minus j omega, because that is the Euler form. So what happens is when I'll talk about only the positive, and then I'm going to get that Euler form because that is now my cos omega. So applying the Euler form, I get it in this representation. Okay, here I've corrected it. So this is my phase and magnitude. So I have it in my phase and magnitude. So if I am talking about the frequency response of this equation, and then I have to just take the second half of that, that is magnitude of h of omega, and that is going to be my magnitude or frequency response. And my phase is equal to minus omega into m minus 1 by 2. So if I plug in values of omegas, I'll get my phase response, then I get my magnitude response. I can do both my phase response and my magnitude response, and if I put that phase response is going to be linear, no, because it's just directly proportional to omega. So whatever the value of omega is, it's going to get it linearly proportional. The phase is linearly proportional to the frequency. And now I can write the magnitude response to be this. So this is the final equation, and that is also the most important equation for your magnitude response of your FAR filter. M odd. So I got it right here. So I've written M is equal to odd. Good. So this is for my M is equal to odd. Now I can write for my M equal to even also, right? So that's not going to be much different. What will happen? Yeah, my h of m minus 1 by 2 will be 0, and my summation will be from 0 to m by 2 minus 1. So if I make that change there, then I already have my m is equal to even. So this is my odd and symmetry. Then if I am right, I will be writing next odd and anti-symmetry, hopefully. Okay, so I went to my, yeah, even and symmetry. Good. So correct. I'm writing now my even and symmetry. So for my even, what will be the case? Just I told you, right? I've told already how it is going to look like, but I'm just going to derive it for you so that the steps are clear for you. So here I'm going to do the same. I'm going to put my z is equal to e to the power of j omega, and that's going to what my final equation is going to look like is it's going to become 2h of m cos omega into m minus 1 by 2 minus m. Yeah, so that is, so I'll show you the steps here. You can just see it, and so it's more clear for you. So why I have shown you the steps is because if I just write it in one line, you may do the same for your exams, because your exams, these derivations come, derive the FAR magnitude response for your symmetric even, for your symmetric odd, anti-symmetry even. So they can ask the equal probability for all 4 questions to come in your exam. So when that happens, if you do if you do till that step and you don't do this step, you just write the expression from that, you will lose marks. It's not gonna get you marks. So that's why I'm showing few steps here on what happens for my m equal to even, and it is a symmetric case. So both are, so I've done for m equal to even, so it is going to look like this, right? Sigma n equal to 0 to m by 2 minus 1 h of n into 2 cos omega into m minus 1. So I am writing the odd, which was derived first below. So now you have both odd and even for symmetry. This is my m equal to odd. Good. So yeah, derivations come in your exams, written exams mostly, but even for your gate exams, they ask you to find the magnitude response when m is equal to say 1. Then what is maybe not 1, m equal to 3, and then you have to do this. You have to put in m equal to 3, and it will be given whether it is a symmetry or anti-symmetry. And then you have to find the magnitude response, so you have to do it. So all these are important questions, and important areas from where you get questions. So the next is what is remaining. So we have done 2 equations for your magnitude response. So 2 more is pending, which is your anti-symmetry, even and odd. So for your anti-symmetry, it's going to be minus the first half of the filter is going to be equal to the second half of the filter, negative of the second half. So that minus is going to there, and minus is going to be there, and the Euler representation for my minus e to the power of j theta minus e to the power of minus j theta is equal to 2j sine theta. right? So I am going to have a sign representation. So the next two equations I can tell it's going to have my sign representation, and I'm going to take the j, right? I'll be getting a j because my e to the power of j theta minus e to the power of minus j theta is equal to 2j sine theta, and j will be taken as e to the power of j pi by 2. Because when I take it as e to the power of j pi by 2, that is cos pi by 2 plus j sine pi by 2, that is equal to j. So j can be written, my imaginary variable j can be written as e to the power of j pi by 2. I'll be showing that 2m minus 3 by 2 h of n into 2j. See, this is the Euler formula I'm having for e to the power of, right? So in this Euler form, the j can be written as e to the power of j pi by 2. So that is your cos pi by 2 plus j sine pi by 2, because the Euler formula is e to the power of j theta is cos theta plus j sine theta. What happens is I get my e to the power of j theta minus e to the power of minus j theta, and that's going to come out to be 2j sine theta. So that is the Euler formula, and that is exactly what I'm going to use here. So in this case, it's going to be omega into m minus 1 minus 2n by 2, and that's going to come out to be omega into m minus 1 by 2 minus n, right? So this is for your anti-symmetry. So anti-symmetric you have cos, and for your anti-symmetry you have. Another thing I want to tell you here is my center of symmetry term. So why no this it is necessary only because I want to take my j as j outside. My imaginary variable j, I want to take it as e to the power of j pi by 2 outside. So I'm gonna show how. But what I can tell is that the generally by logic we speak, my anti-symmetry means my first half of the signal is equal to the negative of the second half. So which means at the center of symmetry for m equal to odd, I'm going to get my positive value and negative value aligning each other on top of each other. So h of m minus 1 by 2 and minus h of m minus 1 by 2. So this both are right. So they are going to cancel. Good. H of m minus 1 by 2 and minus h of m minus 1 by 2, and that is 0. So I can practically I can say that the center of symmetry will be 0 because my plus and minus values at that point will cancel each other. So that is why for my anti-symmetry frequency response, you don't have to take the e to the power of j omega m minus 1 by 2. So n equal to 0, m minus 3 by 2, h of n 2j sine omega into m minus 1 by 2 minus n. So now that h of m minus 2 by 2 has been made 0. Now why I did that was, even if I didn't do that, it wouldn't have, was not needed. But by doing so, I am now able to represent my j as e to the power of j pi by 2, because the Euler formula for e to the power of j theta is cos theta plus j sine theta. So that's going to come out to be cos pi by 2 plus j sine pi by 2, and that is equal to j. So which means I can now write it as e to the power of j pi by 2 and take that e to the power of j pi by 2 outside, which means my phase is going to be, because of that negative, I'm going to have a phase shift of pi by 2 added, and that is the only difference. So my phase is now going to be pi by 2 plus it's going to be just pi by 2 minus omega into m minus 1 by 2. So that is your phase, and the magnitude is what is given on this side. So this is your magnitude. M is equal to, this is for m equal to odd, and then for my anti-symmetry, m is equal to even. I can write the same thing, only thing is my summation will be from 0 to n by 2 minus 1. So pretty much you have 4 equations, but only 2 are, they are all, I would say, like they are all very identical, except that for symmetry you have cos and anti-symmetry you have sine. That is the only difference in the summation and other things. Everything can be correlated. So you learn one, the other 3 should be, you should find way to remember the other 3 very easily. So from this, I can write my magnitude response for m equal to odd as this, what we just derived. And then am I writing my m equal to even also here? Yes, I can write, because it is going to be the same. Yes, I'm doing it. It's m by 2 minus 1 h of n 2 sine omega m minus 1 by 2 minus n. So that is for my m equal to even. So what So we have seen the FIR representation for M odd, M even. We have seen symmetry, anti-symmetry, and also the magnitude response for all four types, type 1, type 2, type 3, and type 4. And now we'll be doing numericals on these in our next class. Thank you. See you then.